So moving on, one of the things that we can show that's really important is that if b is an integer greater than 1, then any positive integer n can be represented uniquely using this integer b as what we call the base of the number. And this is in the form n is equal to a naught plus a1 times b plus a2 times b squared all the way up to ak minus 1 times b to the power k minus 1, where k is a positive integer and a naught through ak minus 1 are all non-negative integers less than b. AI is strictly less than b and is greater than or equal to 0. And you may not have realized it, but this is something that you're already familiar with in the sense of decimal or base 10. So when you write down the number 123, what this is really meaning is 1 times 10 squared plus 2 times 10 to the power 1 plus 3 times 10 to the power 0, or 1. So this is called a decimal expansion of a given number when we use 10 as our base. Each of the coefficients in any number decimal is between 0 and not equal to 10, but 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And the idea is that there are many number systems that are more suitable to use in various applications in computer science, such as binary or base 2, octal or base 8, and hexadecimal or base 16. So for example, give you a binary example. If you take the number 1, 0, 1, 0, 1, 1, 1, 1, 1, in binary, this is the number 1 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 squared plus 1 times 2 cubed plus 1 times 2 to the 4th plus 0 times 2 to the 5th plus 1 times 2 to the 6th plus 0 times 2 to the 7th plus 1 times 2 to the 8th. And you can very clearly see how the decimal expansion is very, it's the same idea in binary, only in binary we're using base 2. So in binary we have that the coefficients are between 0 and strictly less than the base, which is 2. So our coefficients can only be 0 or 1. And sure enough, when you go through and calculate this number in decimal, this is going to end up equaling the number 351. An example of octal, or base 8, is given by, we'll do the number 7016 base 8. This is going to be 6 times 8 to the 0 plus 1 times 8 to the power 1 plus 0 times 8 to the power 2 plus 7 times 8 to the power 3, where each one of the digits in the number is strictly less than the base, which is 8. And when we go through and calculate this number, this is going to end up being the integer in decimal 3,598. And lastly, I'll do an example of hexadecimal. And to do hexadecimal, we actually need to make a little bit of a definition. And this is typically a condition that's used when we're expressing things in hexadecimal, because a hexadecimal expansion, we require numbers greater than 10 for our coefficients, so possibly equal to 10 as well. What we have in binary, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but because the hexadecimal digits can be any digit from 0 up to 15, we have to introduce symbols for the integers 10, 11, 12, 13, 14, and 15. And typically what we do is we call these just by the first few letters of the alphabet. So A, B, C, D, E, and F are used in hexadecimal to represent the numbers 10, 11, 12, 13, 14, and 15. So if you see something like 2A, E, 0, b in hexadecimal, or base 16, this means the number b times 16 to the 0 plus 0 times 16 to the power 1 plus b times 16 to the power 2 plus a times 16 to the power 3 plus 2 times 16 to the power 4, where b is 11, e is 14, a is 10. So when you compute this number, you end up getting this is 175,627. So with these examples and this theorem that we've introduced at the very beginning of the video, I'm hoping that you can clearly see that there's this very, very deep connection between these alternative expressions of integers and the division algorithm introduced in part 1. Specifically, we can do base conversion for the bases of numbers very easily using the division algorithm. Specifically, given n, we can divide n by the base b to obtain a quotient q naught and a remainder r naught. Specifically, n will be q naught times b plus r naught. R naught is a remainder, so r naught is going to be strictly less than b and will be greater than or equal to 0. And thus the remainder is actually equal to the first place in the base b expansion of the number. Specifically, if we come up and look at some of these examples that we did here, if you divide 351 by 2, you get that 351 is equal to 2 times 175 plus 1, and the first digit of this expansion is exactly equal to 1. Likewise, 3,598 is going to be equal to 449 times 8 plus 6. The first digit of the octal expansion. And 449 is the quotient in this division of 3,598 by 8. And if you do this for hexadecimal, right, you'll end up getting that the remainder upon division of this number by 16 will end up being b, or 11. So the procedure here is very, very effective, and not only that, right, we can continue this procedure to get all of the base b digits of a given number. If we continue on to divide q naught by b to obtain q1 times b plus r1, where r1 will be between 0 and not equal to b, but up to b minus 1. You divide q1 by b to get q2 times b plus r2. And so on and so forth, all the way down to q n minus 1 is equal to q n times b plus rn where rn is between 0 and b, and we stop when we finally get to a zero divisor, or zero quotient of our number. We stop at the divisor qn is equal to 0, and then our integer n will be equal to rn minus 1, rn minus 2, all the way to r2, r1, and r0. And so going back to our binary example from before, where we're going in the reverse direction. The first decimal digit is a 1, and the remainder of division of 351 by 2. The division of 175 by 2 gives us 87 times 2 plus 1, which means the next digit should be a 1. 87 is 43 times 2 plus 1, which is this one right here. 43 is equal to 21 times 2 plus 1, which is this one right here. 21 is equal to 10 times 2 plus 1, which is this one right here. 10 divided by 2 is 2 times 5 plus 0, which is this 0 right here. 5 is equal to 2 times 2 plus 1, which is this 1 right here. 2 is equal to 1 times 2 plus 0, which is this 0 right here. And then lastly, 1 is equal to 0 times 2 plus 1, which is this one right here. So for the octal example that we presented earlier, if we want to move backwards, we showed that 3,598 is 449 times 8 plus 6, which is the first decimal or the first digit in the octal expansion of this number. The next digit will be 449, which is the quotient here, divided by 8, which is 56 times 8 plus 1, gives us a 1 in the next digit. 56 divided by 8 will end up being 7 times 8 plus 0, so a 0 remainder, which is this digit. And then lastly, 7 is equal to 0 times 8 plus 7, so the final digit is going to be a 7, and we stop the algorithm because our quotient hits 0. The last one is the hexadecimal example that I went over, and this is a relatively large number, but if we go through and divide 175,627 by 16, we end up getting that this is going to be 10,976 times 16 plus 11, or b, which is the first digit in this expression. Dividing 10,976 by 16 gives us 686 times 16 plus 0, which is the next digit in this expression. 686 divided by 16 gives us 42 times 16 plus 14, or e, which is the next digit. 42 is equal to 2 times 16 plus a, or 10. So a is the next digit. And lastly, 2, when you divide it by 16, is 0 times 16 plus 2, which gives the last digit here as 2. And this terminates the expansion because we've reached 0 for our quotient. So I think these three examples very clearly show this process. And the main reason this is working is because if you take your first factoring here for finding your first digit in a base b expansion, and you use the subsequent definitions, so this is going to say that n is equal to q1 times b plus r1 times b plus r0. Then the next step gives you q1 here is q2 times b plus r2 times b plus r1 times b plus r0. And if you continue this all the way down, what you're doing here, each time you apply this division algorithm, is you're essentially kind of pulling out the remainder term in the division by b, and if you multiply this right here, you'll get r1 times b. Then you also have to multiply this by b, which will give you b squared here times r2, and so on and so forth, all the way down to the very end. And you get that polynomial expression for n in terms of base b. So there's really nothing fancy going on here. It's just very, very nicely using the division algorithm to pull out each one of these remainders. And this is the big connection between different bases of a given integer and the division algorithm that we introduced earlier. And so in the book, this algorithm is described in a very straightforward manner using pseudocode, and there's also a very nice table illustrating the different comparisons up to 15, number 15, between all of these different representations of integers. So I definitely think you should take a look at that. So for example 111 base 2 is going to be 1 plus 2 plus 2 squared, which is 7. It's 7 in decimal, 7 in octal, and 7 in base 16. So it has hexadecimal. Look at 111 base 2. This is 1 plus 2 plus 2 cubed, which is going to be equal to 15. In decimal, or f in hexadecimal, or 17 in octal, And if you look at this table for a little while and you kind of think about these conversions, you should see that there's a relatively straightforward manner to convert from binary, octal, and hexadecimal to one another. And I'll illustrate this with an example. So if you take the number 111110 10111100 base 2, and I want to convert this to octal. If I group these digits in threes, with adding an extra 0 to the very end if I have to, which doesn't change the number, this will be 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, and I calculate what each one of these numbers is in octal. Each one of these numbers is going to be from 0 to 7, which are directly the octal digits. So this will be 3, this is 7, this is 2, this is 7, and this is 4. So this number is the number 37274 base 8. And there's a directly similar procedure for hexadecimal. This is directly, using these two things that I showed before. 1111 is 15, just our number f. So for hexadecimal, instead of grouping in threes, we group in fours with extra 0 padding on the end if we have to. This will be 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, which is going to correspond to the hexadecimal number. This is 3, this is E, this is B, and this is C. So it's this is the number, the hexadecimal number 3EBC, base 16. You can even do this trick in the reverse direction. So if you have 765 base 8, this is going to be the same thing base 2 as 111, 110, 101. And for hexadecimal, if you have the number ABD, this is going to be equal to 1010, 1000, 1101, base 2. So because of these nice relationships, there's no need to convert to decimal and then, sort of from octal to decimal and from decimal to hexadecimal. You can just really go straight from in between any one of these, which is very, very neat. So next I want to describe how to add and multiply integers of different bases. So we'll start with addition. Suppose A is the number an minus 1, an minus 2, all the way to a naught, base B, and C is the integer cn minus 1, cn minus 2, all the way to c2, c1, c naught, base B. We know that A plus C is the same thing as the summation of AK B to the K for K from 0 to n minus 1, and C is just the summation K equals 0 to n minus 1 of ck times b to the power k. And it's important through all of this that you remember these numbers have to all be strictly less than b. Same thing with the ck's, they have to be strictly less than b. Because they're the digits of our number in the base B representation. So from rules for adding finite sums, this is going to be the same thing as AK plus CK times B to the K, summed from K equals 0 to n minus 1, which is A naught plus C naught plus A1 plus C1 times B to the 1 plus A2 plus C2 times B squared, all the way up to and including the term an minus 1 plus cn minus 1 e to the power n minus 1. And so our algorithm for computing this should be relatively straightforward and should be based on this and the ideas that we've developed so far. Specifically, this integer a naught plus c naught in general is not going to be less than b. A naught plus c naught is in general, it's nice if it's less than b, but in general it's going to be greater than or equal to b, which means that in order to express this sum as a base B representation, we're going to get some extra value here that gets carried over to this term right here. So the first step in the algorithm is to divide this a naught plus c naught by b, and we say that this is going to be k naught times b plus r naught. So the remainder of this division is the first digit, because we know that r naught is going to be strictly less than b and greater than or equal to 0. And what's going to be carried over from this term into the next term up is going to be k naught times b. So what we have to do then is divide a1 plus c1 plus k naught by b to obtain some k1 times b plus r1, where r1 will be guaranteed to be less than b. So r1, the remainder in this division, is going to be the true first component of this number. The 0th component is going to be r naught. And this process is going to continue. It's going to continue all the way up until we have an minus 1 plus bn minus 1 plus k n minus 2 and this is going to be equal to k n minus 1 times b plus r n minus 1, where r n minus 1 is going to be strictly less than b. But depending on this value k n minus 1, we might even have that this value k n minus 1, which is the remainder term that gets carried over all the way up to this last term right here, could be greater than b. In that event, you have to continue to divide by b up until we get that km is equal to 0 times b plus remainder rm, where rm is strictly less than b, and thus the addition of a and b, or a and c, base b, will be the listing of all these remainders. The algorithm is just strictly based off of the ideas that we've developed before and connecting them with the algebraic representation of these numbers in terms of finite sums. So if we apply this algorithm base 2 to add the numbers 1, 1, 1, 0, and this is our A and our B, we'll take 1, 0, 1, 1. A plus B is going to be equal to 1 plus 0 is 1, 1 plus 1 is 2, or 0, and then we have to carry over a 1 to the next term, where we have 1 plus 0 plus 1 is 2, so again we have to carry over, and then we get 1 is carried over, plus 1 plus 1, which again is going to be 1 plus 1 is 2, plus 1 is 1, so we'll have a 1, and then we have to carry over another 1. Or in step-by-step form, right? 1, 0 plus 1 is equal to 0 times 2 plus 1. So this is our first digit. The next is going to be 1, 1. So 1 plus 1 plus 0. This is equal to 2, which is 1 times 2 plus 0. And the next two digits are 1 and 0. So 1 plus 0 plus the quotient term here, which is a 1, which is equal to 2. That's 1 times 2 plus 0. and the next digits then are going to be 1 and 1. So it's 1 plus 1 plus the quotient from the previous division, which is 1. This is equal to 1 times 2 plus 1. Then lastly, our quotient term here is 1. And 1 is equal to 0 times 2 plus 1. And what we're left with is the number 10011, which is the same as our quick calculation before, just having applied the algorithm. What's super interesting here is you can also use standard addition algorithms that you learned in grade school for adding decimal numbers with the added restriction that you have to mind the base. Oops, and I just realized there should be a C right here. I apologize for the typo. So for example, if I want to multiply 110 by 1011, so if I want to add these two integers together, base 2, I start with the 0th order term, which is 0 plus 1, or 1. The next order up is 1 plus 1, which is 2, or 0, with a carryover of 1. 1 plus 0 plus 1 is going to be again 2, which is 0, but a carryover of 1. And then 1 plus 1 is 2, which is 0, a carryover of 1, but plus this other one right here gives me a 1. And then 1 plus 0 is 1. And I'm left with the exact same value that I got before. So this is very neat, and it clearly shows, right, the consistency of what we're doing here. For multiplication, we have a similar procedure. It is a little bit longer, but it's not too difficult to understand. So we'll take A and C as before and try and calculate A times C. This is going to be the summation from K equals 0 to n minus 1 of AK times B to the K times the summation from K equals 0 to n minus 1 of CK times B to the K. And what we want to consider here is what we get when we multiply summations together algebraically. We know that for two terms in the sum, A plus B times C plus D, for instance, will be A times C plus A times D plus B times C plus B times D from a FOIL. And if we do this foiling out, but for general summations now, this is going to be expressible as a double summation. And perhaps it'll be a little bit more clear if I change the index of one of these sums, sum from I equals 0 to n minus 1 of ai b to the I. It'll change the index of this sum to be j. So when I FOIL these out, I'm going to get actually a double summation over I and j of ai times cj times b to the I times b to the j, which is b to the power I plus j. Or written out term-wise, this will be a naught times c naught plus a1 c naught plus a naught c1 times b to the 1 plus a1 times c1 plus a naught times c2 plus a2 times c naught b squared, all the way up to and including the final term, which is going to be when I equals n minus 1 and j equals n minus 1. So this will be a n minus 1, c n minus 1, and I plus j will be b to the power 2n minus 2. And so to help us simplify a little bit, I'm going to introduce an expression s for the coefficients here. A times c is going to be s naught plus s1 times b plus s2 times b squared, and so on and so forth, all the way up to s2n minus 2 times b to the power 2n minus 2, where si here is just equal to a naught times ci plus a1 times ci minus 1 up to ai times c naught, or si is the summation from k equals 0 to I of ak times c I minus k. And for our algorithm, we just go through and do the exact same thing as before that we did for addition, which is just use the division algorithm multiple times to compute the carryovers in each subsequent step of this addition right here. Because in general, s naught will be a value that's greater than or equal to b. In order to express this s naught base b, we need to have just the remainder of the division by s naught and carry over the extra value into s1 times b right here, and so on and so forth. So the algorithm here is going to be to divide s naught by the base, and then s1, the next coefficient, gets an additional k naught from this term right here, s naught. And then this term right here when we divide S1 plus K naught by B, this S1 will give us just an R1 for our first entry in this number, and then carry over K1 times B into the next iteration. So this will be S2 plus K1, which we then have to divide by B to get K2 times B plus R2, and so on and so forth, all the way up to S2n minus 2 plus K 2n minus 3 is equal to K 2n minus 2 times B plus R 2n minus 2. But in general, we can't stop here, because even though R 2n minus 2, right, is less than B, strictly less than B, in general, we don't know if this K2n minus 2 is 0, and typically it's not. So we have to continue this procedure until we get that Km is equal to 0 times B plus Rm. And then the sequence of remainders is the sequence of digits in the base B expansion of this multiplication. So the number A times C base B will be Rm minus 1 all the way down to R2, R1, R0. And so to illustrate this idea out in an example, let's go through and compute this. And we'll use the numbers A is equal to 110 base 2, and C is equal to 101 base 2. So to illustrate the first thing that I showed above, we'll just go through and do this brute force. 2 to the 0, 1 times 2 to the 1, plus 1 times 2 to the 0, then 1 times 2 to the 0, plus 0 times 2 to the 1, plus 1 times 2 to the 2. And when we cross multiply all these terms, we get 0 times 1 times 2 to the 0, plus 0 times 0 plus 1 times 1 times 2 to the 1, plus 1 times 0 plus 0 times 1 plus 1 times 1 times 2 to the 2, plus 1 times 1 plus 1 times 0 times 2 to the 3, plus 1 times 1 times 2 to the 4. Which we very quickly see is 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2 plus 1 times 2 to the 3 plus 1 times 2 to the 4, or base 2, the number 11110. Now, applying our algorithm is a little bit faster here. And in general, it's much faster, because what we need to do is say, so S0 is going to be 0 times 1. We need to expand this, which is going to be 0 times 2 plus 0. S1, and the S here, I'm just using this formula in general. So S1 is going to be the first entry in A, case 0 times the second entry in C, so it's 0 times 0 plus the second entry in A times the first entry in C, which is 1 times 1, plus the quotient from the first division, which is 0. And so this will be equal to number 1, which we know is going to be 0 times 2 plus 1. And then S2 is going to be equal to 0 times 2, 0 times 1, sorry, 0 times the second expansion digit in C, so it's 0 times 1 plus 1 times 0 is the first in each of them, plus the second in A and the first in C, which is 1 times 1, plus the remainder term in the previous step, which is just going to be 1 again. So this is 0 times 2 plus 1. S3 is going to be the 0th term in A times the 3rd term in C, 0 times 1, the 3rd term in A times the 1st term in C, which is 1 times 1, and then plus the holdover, the carryover from this operation right here, which is 0. So this is going to be 1, which we know by now is 0 times 2 plus 1. And then lastly, we have to consider S4, which is just going to be equal to the final terms multiplied together. So 1 and 1. And we have to add to that the carryover from the last step, which is 0. This is equal to 1, so it'll be 0 times 2 plus 1, and there's no more carryover, so we can stop the algorithm, and we're left at the number 11110, which is these remainders, base 2. So this is another way of calculating this multiplication. And the final thing that I want to point out here, that just like before, if you want to multiply two numbers of any base, you can do it using the basic algorithm that you learned from grade school. So if we do 110 times 101, remember that the algorithm from grade school says that we can do this by first doing 0 times 1, which is 0, 1 times 1, which is 1, 1 times 1, which is 1, and then moving over a digit place and computing the next multiplication step. So we'll have a 0 here. We got to do 0 times 0, which is 0, 0 times 1, which is 0, 0 times 0, which is 0. And then you can do the final multiplication step by moving over to this final digit place right here. You do 1 times 0, which is 0, 1 times 1, which is 1, and 1 times 1, which is 1. And if I add the result together, we're left with 0, 1, 1, 1, 1, which is the same base 2 expansion that we found using the previous two methods. So I think this is clear enough and should kind of help you understand exactly how to do multiplication with respect to any base that you ever need to do multiplication for.